It is indeed legal to place multiple motors on a single starter with individual overloads, but only one circuit breaker and contactor, but it's essential to adhere to specific conditions outlined in the National Electrical Code, or NEC. Section 430.86 of the NEC addresses group installations. It states that several motors, each not exceeding a nominal 1 horsepower rating, may be grouped under the protection of a single branch circuit short circuit and ground fault protective device, provided the total branch circuit ampere rating does not exceed 20 amps for continuous duty motors and 15 amps for non-continuous duty motors. Section 430.90 B discusses motor controllers, specifying that each motor shall be provided with a motor controller such as a starter, running overcurrent protective device, service switch, or circuit breaker that serves as both a controller and motor branch circuit short circuit and ground fault protective device for motors connected in accordance with 430.90. F through E. Section 430.90 C covers motor controllers for motor groups, stating that where 2 or more motors are connected to a single motor controller, each motor shall be protected by an individual overcurrent protective device in series with the motor controller except as provided in 430.86. Now let's consider the interpretation of these codes for your specific scenario. Multiple motors with individual overloads can be connected to a single starter with one circuit breaker and contactor if firstly, the total horsepower rating of the motors does not exceed the horsepower rating of the starter. Secondly, the individual overloads are sized according to the nameplate current of each motor. Thirdly, the circuit breaker is sized to protect the starter and the wire feeding the starter. Fourthly, the starter is listed and rated for group installations. For example, you could install 4 5 horsepower motors on a single 25 horsepower starter with individual overloads. Provided the starter is listed for group installations, the overloads are sized for each motor, and the circuit breaker is sized to protect the starter and wire. Here's a more detailed breakdown of what to consider. Firstly, concerning the NEC requirements, Article 430 provides comprehensive guidelines for motor circuits, motor control, and motor protection. These regulations are designed to ensure safety and prevent electrical hazards. Secondly, regarding group installations, NEC Section 430.86 specifically addresses the conditions under which multiple motors can be connected to a single branch circuit. This allowance is typically limited to small motors. Thirdly, on individual motor protection, each motor must have its own overload protection to prevent damage from excessive current draw. These overloads are sized based on the motor's nameplate current rating, ensuring that each motor is protected according to its specific requirement. Fourthly, talking about the short circuit and ground fault protection, the circuit breaker serves as the primary protection against short circuits and ground faults for the entire circuit. It must be appropriately sized to protect the starter and the conductors feeding the motors. The breaker's ampere rating should be coordinated with the starter's rating and the conductor's ampacity. Fifthly, considering the motor controller, the starter acts as the motor controller, providing the means to start and stop the motors. It must be suitable for the group installation and capable of handling the combined load of all connected motors. Sixthly, speaking on the importance of the starter rating, the starter must be rated for the total horsepower of all motors connected to it. This ensures that the starter can handle the combined load without overheating or failing. If the total horsepower exceeds the starter's rating, the starter may not function correctly and could pose a safety hazard. Seventhly, looking into the overload protection sizing, the overload relays or heaters must be sized according to the nameplate current of each motor. This is critical for protecting each motor from overcurrent conditions that could cause damage to the motor windings. Sizing the overloads correctly ensures that the motor will be disconnected from the power supply if it draws excessive current. Eighthly, considering the circuit breaker sizing, the circuit breaker must be sized to protect the starter and the conductors feeding the starter. The size of the circuit breaker is determined by the starter's specifications and the ampacity of the conductors. It is important to consult the NEC tables and manufacturer's instructions to determine the correct breaker size. Ninthly, on the listing and rating for group installations, the starter must be listed and rated for group installations. This means that the starter has been tested and approved for use with multiple motors. The listing ensures that the starter meets specific safety and performance standards for group installations. 10thly, let's not forget about the conductor sizing. The conductors feeding the starter must be sized to handle the total load of all motors plus any additional loads on the circuit. The conductor ampacity must be sufficient to carry the continuous load without overheating. NEC Table 310.15 provides guidance on conductor ampacity based on conductor size and insulation type. 11thly, the control circuit considerations. The control circuit for the starter must also be properly protected and sized. This includes the wiring for the start-stop buttons, limit switches, and other control devices. The control circuit should have its own overcurrent protection to prevent damage from short circuits or ground faults. 12thly, about the horsepower versus amperage. It's important to understand the relationship between horsepower and amperage. Horsepower is a measure of mechanical power, while amperage is a measure of electrical current. The amount of current a motor draws is related to its horsepower rating, but it also depends on the motor's voltage, efficiency, and power factor. 13thly, on the documentation and labeling. All components of the motor circuit must be properly documented and labeled. This includes the starter, circuit breaker, overloads, and conductors. Proper labeling helps to ensure that the circuit can be easily identified and maintained. 14thly, the local codes and regulations. In addition to the NEC, local codes and regulations may also apply to motor installations. It's important to consult with the local electrical inspector to ensure that the installation meets all applicable requirements. 15thly, speaking on the qualified electrician, it's important to have a qualified electrician perform the installation and wiring of the motor circuit. A qualified electrician has the knowledge and experience to ensure that the installation is done safely and correctly. They can also help to ensure that the installation meets all applicable codes and regulations. 16thly, the NEC tables and calculations. The NEC contains numerous tables and calculation methods for determining the correct size of conductors, overloads, and circuit breakers. These tables and calculations are based on factors such as the motor's horsepower rating, voltage, and duty cycle. 17thly, on the example scenario, consider an example where you want to install 4 5 horsepower motors on a single starter. Each motor has a nameplate current of 7.6 amps at 460 volts. The total current draw of all 4 motors is 30.4 amps. The starter must be rated for at least 20 horsepower, and the circuit breaker must be sized to protect the starter and the conductors feeding the starter. The overloads must be sized for 7.6 amps each. 18thly, the potential issues and troubleshooting. Potential issues with motor circuits include overloads tripping, circuit breakers tripping, and motors overheating. Troubleshooting these issues requires a systematic approach to identify the cause of the problem. Common causes include undersized conductors, improperly sized overloads, and motor problems. 19thly, considering the energy efficiency. Energy-efficient motors can help to reduce energy consumption and save money on electricity bills. When selecting motors for a group installation, consider using energy-efficient motors to minimize energy costs. 20thly, on the maintenance and inspection. Regular maintenance and inspection of motor circuits are essential for ensuring safe and reliable operation. This includes inspecting the conductors for damage, testing the overloads and circuit breakers, and cleaning the motors to prevent overheating. 21stly, about the safety precautions. Always follow proper safety precautions when working with electrical equipment. This includes wearing appropriate personal protective equipment such as gloves and safety glasses, and energizing the circuit before working on it. 22ndly, about the understanding of motor types. Different types of motors have different characteristics and requirements. It is important to understand the type of motor being used in the installation to ensure that it's properly protected and controlled. Common motor types include induction motors, synchronous motors, and direct current motors. 23rdly, let's talk about the starter types. There are different types of motor starters available, each with its own advantages and disadvantages. Common starter types include across-the-line starters, reduced voltage starters, and soft starters. The type of starter used depends on the motor size, the application, and the electrical system. 24thly, on the reduced voltage starting methods can be used to reduce the inrush current when starting large motors. This can help to prevent voltage dips and reduce stress on the electrical system. Common reduced voltage starting methods include autotransformer starting, reactor starting, and part winding starting. 25thly, we have the harmonic considerations. Motors can generate harmonics, which are distorted waveforms that can cause problems in the electrical system. Harmonic filters can be used to mitigate the effects of harmonics. 26thly, about the power factor correction. Power factor correction capacitors can be used to improve the power factor of motor circuits. This can help to reduce energy consumption and improve the efficiency of the electrical system. 27thly, about the motor enclosures. Motor enclosures are designed to protect the motor from the environment. The type of enclosure used depends on the application and the environment. Common enclosure types include open drip-proof, totally enclosed fan-cooled, and explosion-proof. 28thly, about the motor insulation. Motor insulation is designed to protect the motor windings from electrical breakdown. The insulation class determines the motor's maximum operating temperature. Common insulation classes include Class A, Class B, Class F, and Class H. 29thly, we have the motor bearings. Motor bearings support the rotor and allow it to rotate smoothly. Bearings must be properly lubricated to prevent wear and failure. Common bearing types include ball bearings and roller bearings. 30thly, we have the motor cooling. Motors generate heat during operation, and they must be cooled to prevent overheating. Common cooling methods include air cooling and liquid cooling. 31stly, let's talk about the motor vibration. Motor vibration can be caused by a variety of factors, including imbalance, misalignment, and bearing problems. Vibration can lead to premature wear and failure of the motor. 32ndly, let's get into the motor testing. Motor testing is performed to verify that the motor is operating correctly. Common motor tests include insulation resistance tests, winding resistance tests, and surge tests. 33rdly, about the motor repair. Motor repair involves repairing or replacing damaged components of the motor. Common motor repairs include replacing bearings, rewinding the motor, and repairing the motor enclosure. 34thly, about the motor replacement. Motor replacement involves replacing the entire motor with a new or refurbished motor. This is typically done when the motor is beyond repair or when it's more cost-effective to replace it than to repair it. 35thly, about the motor efficiency standards. Motor efficiency standards are designed to promote the use of energy-efficient motors. These standards require motors to meet minimum efficiency levels. 36thly, about the motor management programs. Motor management programs can help to reduce energy consumption and improve the reliability of motor systems. These programs involve tracking motor performance, performing regular maintenance, and replacing inefficient motors. 37thly, let's get into the motor life cycle costs. Motor life cycle costs include the initial cost of the motor, the cost of energy to operate the motor, and the cost of maintenance and repair. When selecting motors, it's important to consider the life cycle costs to minimize the total cost of ownership. 38thly, let's not forget about the environmental considerations. Motors can have a significant impact on the environment. Using energy-efficient motors and properly maintaining motor systems can help to reduce the environmental impact. 39thly, let's talk about the future trends in motor technology. Future trends in motor technology include the development of more efficient motors, the use of advanced control systems, and the integration of motors with the Internet of Things. And 40thly, consulting with a qualified electrician. It's always important to consult with a qualified electrician to ensure that the installation meets all applicable codes and safety standards. They can provide valuable guidance and expertise to ensure a safe and reliable installation.